Hello, everyone. Welcome back to our RISE online seminars. Today, Ahmed will talk about confidentiality-preserving smart contracts. So, Ahmed, the floor is yours.
Thank you, Lodovico, for the presentation, and hello, everyone. Today, I will be presenting, as Lodovico said, confidentiality-preserving smart contracts. I am Ahmed Lekssays from the University of Insubria in Italy. So for the outline of this presentation, first I will introduce you to this topic, then I will give you some key elements about like what we will be talking about, especially regarding blockchain, trusted execution environment, etc. By talking about trusted execution environments, I will focus on one paper that's Echid, and I will explain it to you in more details later. But I also included some other approaches that were existing to solve this problem. So in the third point, I will talk about the challenges, and the fourth point about the paper Echid that uses trusted execution environments. Then I will talk about the other approaches to fix to solve this problem, or at least to try to solve this problem. Then I will talk about an implementation perspective by talking about existing technologies, a conclusion, and then references. So first, what is the motivation for having at the first place privacy preserving or confidentiality preserving smart contracts? The first thing is that smart contracts inherit some undesirable blockchain properties, like everything is transparent, and sometimes your computation or there are a lot of examples. For instance, you cannot have some secret on your chain code or your smart contracts. In this program, for instance, you cannot put some private key or something of the sort. The second point is the lack of confidentiality and privacy. As I mentioned, anything that can be private cannot be encoded in a smart contract. This point is also linked to another point that we might discuss later on, like in the questions or something, because it's out of the scope of this presentation, is that smart contracts do not really have an identity. Okay, they are just programs, and they don't have like a key pair, like a private key or something, or they might have public address, for instance, in the case of Ethereum, but they don't have really a private key. So also for the blockchain consensus requirements, some execution might be of some smart contracts might be heavy, which of course leads to a poor performance. So the problem statement, or the problem that we have now, is to design a platform for confidential and performant smart contract execution. So a little bit of background. Of course, smart contracts are just autonomously executed programs, and they are executed by network participants, like in a blockchain, and they need to these participants need to agree on the output of the smart contract after the execution, and also on the state in general. This can lead to a little bit to a philosophical discussion about determinism and non-determinism. So from this small description, you could like infer that smart contracts should be deterministic, because like when they are run at a couple of participants and they need to agree on the output, it is therefore necessarily to be deterministic. This will also lead you to think about smart contracts do not have random functions, for instance, and they don't have any, or at least they shall not have any behavior that might result in a non-deterministic output. This also is linked to some accessing some data structures, sometimes that have some random behavior to access elements, etc. And the second point is the full replication of all nodes. As we mentioned, each participant has his or her own version of the smart contract, and this of course provides fault tolerance and availability. We have also one drawback, that is the on-chain computation is heavy. For instance, I'm making always the analogy to Ethereum because it's the most known, at least now, platform that provides smart contracts. For each instruction in the smart contracts, you pay a fee for it. Okay, so the heavy computations, you pay heavy cost, so they are expensive. Also, the contract state, which is the code, or at least even in the execution of the code, what is saved in the blockchain, and also the user input are public. So, and of course, they are necessary to validate the execution. From all these points, we know that there is a lack of privacy in such technology. We have also another point, and it's trusted hardware with attestation. This is more related. This is not directly related to blockchain, but we will also try to combine them by like in one paper. Just a small introduction. Trusted execution environments, or TEEs, protect the confidentiality and integrity. You can think of them as a part in the CPU that is called the enclave, and like they execute. They have, for instance, it has an identity, since they can have their own private keys and public keys, and they are secure at the level of the hardware, so the operating system itself cannot get access to them. They can also issue some proofs that are called attestations, and these attestations, it's like if they are giving proof that some computation was done correct. There are different vendors for such technologies. One of the most known ones is Intel SGX. It provides a CPU-based implementation of TEs, and they are called enclaves. There is Trust Zone, AMD Trust Zone. It's the same. It fits the same purpose. Also, it is invisible for any entity, like, even as I said, even like the operating system, to generate any attestation. And there is one problem with this technology, is that of course it cannot guarantee availability, because at the end anyone can just turn off the device, and that's it. And so it can terminate the enclave or drop these messages arbitrarily, which is not what we want. So there is a lack of availability. If we compare the two, for instance, for blockchain, there is a lack of privacy, but of course it provides high availability. For this, it provides privacy, but of course there is a lack of availability. So for the challenges that we have now, the first is availability failures for TEs, as anyone can a malicious host can terminate enclaves, and then an honest host could lose, like enclaves in a power cycle or something that's out of the control of the host. Also, there are some security concerns regarding TEs, for instance, side channels, uncovered data leakages, like with side channels. Also, sometimes there are some defenses that are developed, but they are for specific attacks. And also, there is also one line of research that aims to limit the impact, even in case of compromised TEs. We have also one very important point that we usually ignore, which is the time or timer failures. Of course, any TE must trust some time resource, like some external server or whatever. It cannot trust the operating system anyway, because this one, even if it might seem simple to you, but it might create very big problems. For instance, you can imagine that one enclave is generating a block, okay, and other enclaves, like, they generate the same block, but they can delay it because they control the time. So for this TEs, there are some approaches that use some specific protocols, like NEC, if I remember well, to ensure that they have a trusted source for time. There is also one thing that's called proof of publication. For proof of work blockchains, it's the most known one now. The TE must efficiently, of course, verify an item stored in the blockchain, but they need to provide a proof that it was really published by the enclave in the blockchain. And these proofs are signatures at the end. And for instance, in the case of permissioned blockchains, also TEs must be able to validate blocks, as I mentioned, and we need to have a trusted timer, because otherwise we will have a lot of forks in that blockchain, and it cannot work. At the end, an attacker can delay timers responses to prevent an enclave from verifying blockchain content. But there are some solutions, as I mentioned, with TLS enabled NTP servers, network time I think protocol servers, to, like, as a trusted timer, in order to have all enclaves on the same page. Of course, we have also one very important thing, is that the atomic delivery of execution results. Smart contracts are atomic. Everything that, for instance, you can have assertions at any point, where if something fails, like, everything rolls back. It's the same thing in databases. So atomicity of executions, like, as I said, we have two executions, either both of them finish or none of them finish. But we have one problem, that the TEs cannot tell if one state or an input state is a new one, or it was like a stalled state from an old execution. And in this problem, like, an attacker may repeatedly rewind until receiving desired output. In other words, it can try with these old stalled states until maybe some TE believes like this delay in the process it, and of course it gets, for instance, one malicious block published. And also this there is another example where the rewinding could defect the budget-based privacy protection, for instance, like differential privacy. In this point, I will talk more on Echidna, which is a platform for confidentially preserving and trustworthy performance smart contracts. It was published in Euro SNP in 2019, and it's a paper by Oasis Labs in UC Berkeley. By the way, Oasis is also one cryptocurrency that you can check, and they have like a good project. So for this, I will give you just an overview of this technique, because as I mentioned in the introduction, I will focus more on this paper, and then I will compare it with other papers at the end, just briefly, because of time constraints. But of course, in this presentation, I included like pointers to multiple good publications that you might check if you are interested in this topic. So we have, in the architecture of Echidna, we have clients, we have computing nodes, and we have consensus nodes. Okay, we have the first are the clients, which as the end users of the smart contract, the ones that will interact with it. This is these are obvious. Of course, any client can create contracts or executing the ones that are already on chain. We have computing nodes. The compute nodes process requests from clients, and they also run this contract in TEs and generate attestations to prove the correctness of the execution, and of course the state transition and the updates. It is not, of course, not mentioning that these computing nodes, they have trusted execution environments inside them, and they have also the contracts inside these TEs. We have consensus nodes, and they maintain an append-only ledger by running like a consensus protocol. In this case, it might be seen as for Echidn, the description that they have is the proof of work protocol, but from my opinion, it can be extended also to other consensus protocols, because in their architecture they separate, as you see, they separate the computation from the consensus. So the execution is totally different than consensus, which is a good point, which might help this solution to be consensus agnostic. Of course, the contract state and attestations are persisted on blockchain, and they are included there. As I mentioned before, there is a proof of the correct execution and proof of the publication in the blockchain. And yeah, these consensus nodes are responsible for checking the validity of the state using TE attestations. There is one point that is important, and I mentioned it, is that this Echidn is like decouples the execution from consensus. You see, the execution of the contract is totally different than, like, the computing nodes can be even totally different than the what that do consensus, which is really good. For the compute nodes, it can be just one. You don't really need. Of course, if the one is bad, because there is always a single point of failure, but my point is just it can work with one. Okay, but of course, if we have just 2 or 3 that are distributed in a good geographic location, and they have the ability to provide high availability, of course it will work. And also there is proof of correct execution, and of course it's just a set of signature. It's just a signature that TE will provide with the as an attestation. And also as you see, the consensus nodes do not really need the trusted hardware or EIS. EIS is the entity that verifies the attestations, and it's Intel attestation service, and it's the one that verifies if it's really correct or not. So we have some security goals that needed to be achieved by this framework. The first one is the correct execution. Of course, you don't want to have like a blockchain where or these computing nodes cannot even execute code correctly, and you are not sure, you cannot trust them about the execution. This is one. So correct execution is one of the main security goals. We have also the consistency, which means at any point in time we have we have only a single sequence, so we don't have forks. We have always one chain or one linked list that states of state transitions that is consistent with the view of each computing node. Of course, you don't need to have, it's the same thing of hard forks, etc. We have a lot of branches in our chain, which makes it inconsistent, which is not what we really want. We have also secrecy, where the echidna guarantees that the state and the input from honest clients are kept secret from all other parties, and this is the main really purpose. And also it is resilient to key manager TE being breached, as I mentioned before. In this paper, like one of the contributions is to limit the impact of compromised TEs. There is also the graceful confidentiality degradation, even some breach, confidentiality breach happens in the compute modes, it provides forward secrecy, as I mentioned, and also reasonable isolation from affected TEs. So it can limit the damages to specific enclaves. Again, but EKID does not prevent, or at least in the paper, they claim that they don't prevent the contract level leakage, which are usually like some bugs in the code or some covert channels or something like that. So for the evaluation, and I will talk about this paper, and sorry, this slide is dense, but you don't need to read it because they are just like a couple of use cases that were evaluated, like some machine learning contracts, like smart building thermal modeling. They model some non-linear least squares, which is just like, think of it as like an algorithm for thermal modeling. We have also tokens, ERC20 tokens, like in Ethereum, poker and crypto kitties, like just games. So for the evaluation, we see, I have always a problem with the right and the left. So this is the right, yeah. Okay, we have throughput, the evaluation in terms of throughput and latency. So for the throughput, you see that we have Ethereum, and there is a baseline, like the baseline just running the algorithm as it is, and also Ekaden, and we see that the throughput here is always high compared to Ethereum. You see that in some parts there is no Ethereum because it was not implemented in such things, especially for the thermal use case. But for the CryptoKitties and ERC20 tokens transfer, etc., they are also included here. And you see that Echidna has in overall a high throughput. For the latency, you see Ethereum and also Echidna, like as a whole architecture, and also this is just the computation. And you see that again, these are the ones that in blue are implemented in Ethereum, but the others are not implemented. And you see that like there is always low latency with the Echid, and for Ethereum there is always high latency. So for the other approach, we have other approaches. We have one thing that I have three that I will talk about, but of different of course technologies. The first ones are zero knowledge proof based approaches. One example is Hawk, which is one of the most known contributions in this field, and it was published in the Security and Privacy in 2016. It has, of course, strong privacy goals that have hiding the amount of the amounts in transacting parties of monetary transfers. So like you cannot see the amounts or of the transfers, etc. It can also hide the contract state from non-participants. Non-participants, the ones that do not run this smart contract, and also supporting private inputs that are hidden from other participants in the contracts. But it also suffers from some limitations. The snarks succinct non-interactive. Yeah, succinct non-interactive. It's a long name. I don't even remember. It requires a prerequisite trusted setup. Of course, every distinct program that contracts implements a new trusted setup, and also the contract requires kilobytes of data to put on chain. It's heavy, and of course, the privacy relies on trusted third parties who gets all the private data. So for secure multi-party computation-based approaches like Enigma, we have, of course, the secure multi-party computation is just a cryptographic technique that allow different parties or multiple parties to compute functions on private input without learning anything about the output. Also, this enables attaching monetary conditions to the outcome of the computation and incentivize, of course, fairness. But multi-party computation-based systems always require active interactive participation of all computing nodes, so they cannot, one of them cannot be shut down, etc. And of course, the cryptographic tools cause high burden, efficiency burden. We have also the off-chain approaches like Arbitrum. They consider smart contracts as VMs, and they run the execution in the state and everything in a VM. The verification is launched in case of a dispute, like you publish, but when someone wants to challenge or sees that something is wrong, it can challenge the execution. When someone challenges the execution, the ones that run the smart contract or that executed the smart contract or the VM need to put a deposit, and the other challenger need to put a deposit, and then one verifier can fix this dispute by verifying the execution of just a couple of instructions, specific instructions, and whoever fails pays half to the winner and the other half for the verifier, so it loses the deposit, and it's also consensus agnostic. For the existing technologies regarding the implementation, we have Hyperledger Fabric Private Chaincode. It's still under development, so it's not really a mature project. The chaincode in Hyperledger Fabric is executed in Intel SGX, and of course it allows to write chaincode applications when data is encrypted, and it can be also accessed just by authorized parties. We have in Hyperledger private data objects. This is not really related to TEs, but it's also a good mechanism, like when only specific part of selected members can interact with these private data objects. The smart contracts policies are enforced through TEs, and also the private data objects are also used in Hyperledger Sawtooth distributed ledger. There is also one framework by Microsoft. It's called Confidential Consortium Framework, and it's an open source project for building new category and highly available and performant applications. And they are also based on multi-party computation, and it leverages on trusted consortium, for we have a trusted member, and they rely on hardware protected execution environments, as I mentioned, TAEs, and of course they achieve high throughput, low latency, and strong integrity and confidentiality. So as a conclusion of this talk, what we need to take from it is just like smart contracts do not have or lack privacy but also T is like availability. So we can use T's in the blockchains, in blockchain, like for confidentially preserving execution. T is like improve the performance of blockchains, and also they preserve privacy. There are many like now frameworks that, or proof of concepts that can be used like in Hyperledger framework, or some Microsoft framework, or the Oasis Labs Ekin is also implemented. There are other approaches that involve different techniques like zero knowledge proof, multi-party computation, and off-chain evaluation of the execution. So thank you for listening. I'm glad to answer any questions, and for the references of my paper, of my talk, they are cited here, and I will share with you, of course, the slides at the end of this presentation. Thank you so much.
Thank you very much, Ahmed.
Thank you.
So are there any questions? If not, I will ask one question, maybe
Sure.
it's not a question. What chance do you give trusted execution environments to actually end up in, let's say, mainstream blockchains? So do you think that in the future, like the Bitcoin of the future or the Ethereum of the future will use this technology? Or do you think that it will stay mostly in these private Hyperledger Fabric style situations?
Yeah, thank you, Ludovico, for the question. It's very interesting. Okay, so for me, what I think. By the way, the Ekin I presented is by Oasis Labs, and they have their own. This is one of the things that they are promoting for their cryptocurrency. Okay, so this confidentiality preserving smart contracts. So I think the first steps are here. Okay, but for the mainstream deployment, trusted execution environments still face some problems, like side channels, covert channels, etc. So relying on them heavily is still far from like the mainstream adoption. The other thing is that when you add, for instance, some condition like this, it's like if you are compromising decentralization in some way, because you will need that all people running this blockchain to have this hardware, which means like for people who can't get that hardware, they can't really run a node, which is I think, in my opinion, it's against the idea of really having a distributed system at the first place. This is the second point. So the first point was about their security. It's still like not really studied enough. And also there is one. The second point is about decentralization. The third point is about like who you should trust, or we have different vendors. Okay, so these blockchain clients, who should rely on? Intel, AMD, ARM, or what? So this one will have each like technique, like for instance SGX or AMD trust zones. How can you design this blockchain to be compatible with the two? Like maybe you can have some attacks on this vendor, but it doesn't exist on this one. Maybe the architecture itself is different. So regarding your question, like the mainstream adoption is still, we are still far from that point. But for now, for these simple tasks, I think it's good for the moment, and it advances the research in this field. Thank you.
Thank you very much for your answer.
Thank you.
Are there any more questions? If not, then thank you again, Ahmed, for your presentation.
Thank you.
And we will have the next seminar in 3 weeks from now, as usual.
Thank you.